Hey, it's Mr. Kwong here. Let's cover the basics of circuits. So first of all, what is electricity and where does it come from? Well, we remember that atoms are made up of protons, neutrons, and electrons. Protons are positive and they stay in the nucleus with the neutrons, and the electrons are negative and they are in the shells on the outside. And the negative electrons, they are not firmly attached to the atom, but the nucleus is held in very, very tightly by something called the strong nuclear force. So these electrons have the ability to move around under certain circumstances, and they are what cause electricity. In fact, electricity, right? It's where the names come from. They are connected by the same thing. Now, protons are positive, and if they go near each other, they will repel unless they are very close to each other, like in the nucleus. Here they are held together by the strong nuclear force, holds all them together. But otherwise, positives will repel each other. Two negatives will also repel each other. But you know how that saying goes, opposites attract. So a positive, such as a proton, and a negative, such as an electron, they will attract. So if you ever have a situation where you have a material that's um, got lots of positives in it, so say we've got a block of metal and a lot of the electrons have been taken out of it, so all that's left is a bunch of positive protons. Um, this is oversimplification. You can't take all the electrons out of a metal, or at least not easily. So some electrons are taken out, meaning that there's more positives than negatives. There are still, a few negatives in here, but there's more positives. Okay, and you have another chunk of metal, and this one, extra electrons have been added to it. Well, now if you have a little electron floating in the middle here, it's going to be repelled by the negative. So it's going to be pushed to the left by the negative, and it's going to attract to the left by these positives here. So any electrons stuck in the middle, they're going to start flowing to one side. Okay, this flowing is electricity. What is electricity? If these two objects touched each other, um, you would get a little, just before they touch, you'd get a little zap of electricity as these negative electrons from this one, the extra electrons, they move over and appear on the other side. That zap would be like static electricity, where you have an object that's got a buildup of charge, and when it touches the other side, it makes a little zap. All right, so now that we've got some of those basics out of the way, let's think about a battery. So a battery looks something like this, and it's got kind of one end that's colored like this, and this end has a big plus on it, meaning it's positive, and this end down the bottom here has a negative on it. Okay, this is the same thing. One side is positive and will attract electrons, the other side is negative and will push electrons away. So, however, in the middle, inside the battery is a secret insulator which blocks electrons. So electrons can't just travel from negative to positive like this. They have to travel around. Okay. Now, if you're just holding a battery, I've got just happen to have batteries right here. If you're just holding a battery, you can't just, the electrons aren't just going to fly through the air from one side to the other. The air is blocking the electrons too. So you need a wire, right? You need a metal that electrons can move through easily to connect one end to the other. And now the electrons will very happily start moving through this wire to get from one side to the other. Okay, this is the start of a circuit, right? Circuit, like a circle, is something that connects one end all the way around to the other, which is what we've done here. Okay, this is a circuit because it's a full circle, one end connecting to the other, round and round and round. Okay, now there's some rules for circuits, and there's some good reasons why creating this one's not a good idea. Okay, let's talk about circuit diagrams first. I don't want to draw batteries that actually look like this every single time. So we use this to represent a battery, okay, where the long line is the positive side and the short line is the negative side. And that gap in between them, that's that insulator in the middle of the battery. So this in real life looks a bit more like this positive end being like this, and this gap in the middle is this secret insulator inside that blocks electrons from traveling inside. Okay. Now wires we just draw as straight black lines. So I've got a wire connecting one side of my battery and a wire coming out of the other side of my battery. Okay, and then those wires can connect to each other or they can connect to other things. Let's think about one of the common things we use electricity for, which is light bulbs. Now a light bulb sort of in real life might look something like this. Yep. What's going on here is that one side of this light bulb is connected to a wire. The electricity will flow up one side of this wire through this middle bit called the filament and out the other side here. Okay, as those electrons flow through the filament, they actually heat it up, and that heating up releases light energy. Okay, they heat it up because those moving electrons actually rub against the insides of the filament, getting it very, very hot, kind of like rubbing your hands together incredibly, incredibly quickly. Okay, but a light bulb, we represent that like this. We got the wire, that's this wire coming down the bottom here. Then we got a little bump. That little bump represents the filament, and then the wire continues, and the bulb is a circle we draw around the filament. Okay, so that's a light bulb. Now, a switch is a break in the wire, kind of like how we've got a break in the wire here, which is insulating. A switch also has an insulating break. And we draw a switch like this. Let me get rid of this. So the switch I've drawn here has this insulating area in the middle here, this area here of air, which electricity can't flow through. But if we press down on the top of the switch down there, that will close the switch, making it look like this. You can imagine if I've pressed down here, then that's pushed this line down to here, right? Closing the switch, allowing the electricity to move through the wire again. So that is a switch. And this is pretty much all the components we really need for now, and just more wires to connect everything together. Everything can be connected like this. This is now a circuit, not a very nicely drawn one. If I was to draw this out properly, I like to draw things in nice, neat little squares. I can have my switch up like this. There we go. There's a circuit. And we can have any number of batteries or any number of light bulbs or any number of switches. Now, there are some things that we have to keep in mind when creating circuits, because circuits can be dangerous. Electricity can go places you don't want, giving you electric shocks, or you can heat up things. Circuits can even cause fires sometimes if they're done incorrectly. So let's talk about how that happens. And this has a lot to do with current, voltage, and resistance. So the voltage is how strong the push is on the electrons. Now remember what was pushing the electrons? It was this battery. The negative side of the battery is pushing electrons away, and the positive side of the battery is pulling electrons in. So right now electrons are moving from this side, they're getting pushed away, pushed through this light bulb. Oh, this only works if the switch is closed. Let's close this switch. They're being pushed through the closed switch and pulled into the positive side. That's how the electrons are moving. That push and pull is voltage. We use capital V for voltage. And if I have a look at this battery I've got here, somewhere on it, it should say what its voltage is. Oh, there we go. 1.5 volts. It says it right there. I think that looks backwards to you. I think it's mirrored, but it's 1.5 volts. So if I was using this battery, I would say the voltage is 1.5 volts. Now, the current is how many electrons and how fast they are moving through. It's kind of like a current of water in a river. Okay, if you have water flowing, I would say the more water or the faster it's going, that's how much current I've got. Here it's the same, but it's for electrons. How many electrons, how quick are they going? Very, very technically, it's if you look at exactly one point on your circuit and you count how many electrons pass that point, how many electrons flowing past that point every second is your current. And you would say you would have, um, say if you count a lot of electrons, you would say you have a very high number of amps. Okay, for some reason, current is called I. So I is how much current you have, and I might say in this circuit, my current is 1 amp. So I've got 1 amp lot of electrons, which is a lot of electrons. Okay, and you can imagine if there are heaps and heaps of electrons and they're moving very slowly, I'm still counting a lot every second. Or if there's not many, but they're moving really, really quick, then I'm still counting a lot each second. You can also think of it kind of like traffic. If there's a 1-lane road, but the cars are going by really fast, I can count 1, 2, 3, 4, 5 cars go past. Or if it's a multi-lane road, if there's 5 lanes and the cars are going a bit slowly, I might go, there's 5 all at once in 1 second. Same works for current. Okay, and resistance. Think about what part of this circuit might be the resistance. Resistance is sort of working against the current and voltage. It's slowing down the current, pushing back against the voltage. And in this circuit, it is the light bulb. The light bulb is slowing down the current. The current's moving through the light bulb. The light bulb is sucking up some of that energy and using it for itself. So electrons have kinetic energy, that's the energy of movement. And when they go in the light bulb, there's friction. That friction robs them of their kinetic energy. It takes it away, and then they start to heat up the light bulb instead. So we've got kinetic energy turning into heat energy. And the more heat the light bulb gets, eventually it starts getting so hot it glows, and that heat turns to light. So we call that resistance. And resistance, thankfully, is R, makes sense. And we could say the resistance here is a certain amount of ohms. And this one's a bit unfortunate. It looks like a almost completed circle with 2 legs. That is the symbol ohms, which is the units for resistance. I've put a question mark there, but we can actually calculate how much resistance is in this circuit using something called Ohm's law. Ohm's law is an equation that says V is equal to I times R. Okay, voltage is equal to current times resistance. We can rearrange this equation into a couple of different forms. We can say that current is equal to voltage divided by resistance, or we can say that resistance is equal to voltage divided by current. Now, I like this middle form because it makes the most sense to me if I think about what's happening in the circuit. I'm thinking about this current, that's how much electricity is flowing. The more voltage I get, the higher that current is. That is, the more push from the battery, the more the battery is pushing, the more current is flowing. But the resistance, the more resistance I get, the smaller that current gets. Okay, it's pushing against the current, slowing that current down. All right, now we can use this bottom form of the equation to work out how much resistance is in this light bulb because I've got numbers here for my voltage and current. If my voltage is 1.5 and my current is 1, 1.5 divided by 1 is 1.5. So my resistance is equal to 1.5 ohms. So I can put that instead of this question mark, I can say it's 1.5 ohms. Oops, 1.5. Okay, now let's go back to some of these rules for circuit building. Okay, if you ever build a circuit that has no resistance, no light bulb or anything like that. I've just got a battery and it's just connected to wires, and wires have very, very little resistance. So resistance is almost zero. What you have here is nothing is stopping that current from flowing. Nothing's resisting the current. So the voltage pushes electrons, and electrons move as fast as they can. Those electrons move really speedily through this wire. Now the wire um, heats up a little, bit, just like the filament here does. The wire heats up, and it can actually heat up so much that it can cause a fire, or it can cause problems. We call this a short circuit. The reason why it's short is because you can have a normal circuit with a light bulb in it. So here's a circuit, it's got a light bulb, it's not on fire, everything is fine. Let's get rid of this fire. Oops, not like that. Yep, normal circuit, everything's good, light bulb's lit up, right? But if we spill some water or a piece of metal is put into it, maybe this circuit's like a toaster and someone's put a knife into it, which you should never do. Here comes that knife. What's this knife done? This knife has now created a short circuit. It's a shortcut for the electricity. The electricity can now come out of the negative. Instead of going down through the light bulb, instead it can go across the knife and back into the battery. Okay, goes through, short circuit, no resistance, lights on fire. So that's some of the rules of circuit building. You don't want to create short circuits. You want every path the electricity can take to go through some resistance, usually a light bulb or some object that uses it. Okay, let's talk about our last thing, which is series and parallel circuits. These are two different configurations a circuit can have if you've got multiple resistors, like multiple light bulbs. The easy one to think about is if you've got still your circuit, your one big circle, and it's just got multiple light bulbs along the length of it, like this. Okay. Now, multiple light bulbs actually means that you've got less voltage per light bulb, right? It takes the voltage, some effort to push through this one, some effort to push through this one, and some effort to push through this one. So they split the voltage three ways. The other type of circuit is one where instead of just one path for the electricity to take, you actually have multiple paths. So we have our battery and we've got a path around one light bulb here, another path here around another light bulb. So let's just think about these two for the moment before I add in a third. Here we've got our electrons, they're flowing, they're flowing, they're flowing, and then hold on, there's a fork in the road. Some of them are going to choose to go this way, and some of them are going to choose to go this way. Okay, the ones that go down here will go through this light bulb, lining it up, and they'll come back here. The ones that go through here will light up the other light bulb, and then they'll join together. Now notice I drew a lot of electricity flowing up here and not as much down there because the current has to split in two. But now that they've rejoined here, now we've got a high current again, and that high current comes and goes through over here. These guys actually both get to have high voltage, unlike the ones in the series circuit. So this one was series, this one's called parallel. Okay, however, in the series circuit, they got the same amount of current through all light bulbs. Here, the current splits and is shared between them. And if we have another light bulb attached here, the current needs to split even more. It's now splitting three ways. Split comes through, split three ways, and it's much higher out here. Okay, in a parallel circuit, the light bulbs will be much brighter than in a series circuit. Now, both types of circuits have their advantages, but for a bunch of light bulbs, the parallel is actually superior, because what happens if one of these light bulbs breaks, there's a break in there that's blocked the electricity from flowing. So electricity can't flow through here anymore, but that doesn't stop the electricity from flowing before it and flowing around it through the other light bulb. It can still do that. Whereas in the series circuit, if one light bulb is broken, the electricity trying to come through the first one just gets blocked and can't travel anywhere, so all the light bulbs go out instead of just one. All right, I hope you've learned something about electricity. I'm Mr. Kwong. Have a good day.